Hey everyone, and welcome back to G Fun Facts Online. Today, we're diving deep into the world of the super tiny, but with incredibly powerful implications. Imagine being able to see and understand magnetism, not just how strong it is, but its exact direction, all at a scale thousands of times smaller than a human hair. Sounds like science fiction, right? Well, thanks to a remarkable material, it's rapidly becoming science fact. We're talking about a revolution in sensing, and it's all thanks to something called hexagonal boron nitride, or hBN for short. So why is measuring magnetic fields at such tiny scales, the nanoscale, even a big deal? Well, it's key to unlocking secrets in brand new magnetic materials, figuring out how tiny electronic devices called spintronics work, and even, get this, imaging the super faint magnetic signals from biological processes. But here's the catch. Traditional methods to measure magnetism just aren't sensitive enough, or can't zoom in close enough for these delicate nanoscale jobs. We've had some cool quantum sensors, like the nitrogen vacancy center in diamond NV centers for short. They're pretty good, but they have limits. For instance, NV centers usually only measure the magnetic field along one direction. Plus, strong magnetic fields can mess with them if they're not perfectly aligned, and being 3D, they can't get super close to what they're trying to measure, which limits how detailed the picture can be. But what if your sensor was almost flat? That's where 2D quantum materials come in, and they're a total game changer. These materials are, as the name suggests, incredibly thin, sometimes just a single layer of atoms. This means they can get right up close and personal with a sample, potentially giving us atomic scale resolution. And the star of this show, for our purposes today, is hexagonal boron nitride. You might hear it called white graphene, because its structure is very similar to graphene, that other superstar 2D material. hBN has some fantastic properties: a wide bandgap, unique optical and spin characteristics, and it can host stable quantum emitters. All this makes it a dream candidate for quantum sensing. So, what's the secret sauce in hBN that makes it so good for sensing magnetic fields? It comes down to tiny imperfections in its atomic structure, called spin defects. Think of these defects like a specific kind called the negatively charged boron vacancy, or VB-, as tiny quantum reporters. These VB- defects have an electron spin, a quantum property, that we can control and read using light. This technique is called optically detected magnetic resonance, or ODMR. The cool part is that the energy levels of these spins are super sensitive to any magnetic fields nearby. So, by shining light, applying some microwaves, and then carefully measuring changes in the light that the hBN emits, scientists can figure out the strength and the orientation of the local magnetic field. And this is where it gets really exciting. Recent work, particularly from physicists at the University of Cambridge, has shown that specific spin defects in hBN can do something amazing: vectorial magnetometry. This means they can measure both how strong the magnetic field is and its precise direction, all at the nanoscale and at room temperature. This is a huge leap because it gives us a complete 3D picture of the magnetic world at these tiny scales. So why is hBN such a superstar for this kind of detailed magnetic sensing? There are several big reasons. First, multi-axis sensing. Unlike those diamond NV centers that mostly see along one line, certain spin defects in hBN have a kind of lopsided, low symmetry structure. This, combined with how their excited states behave, allows them to detect magnetic fields along multiple axes. True 3D vector measurements. Second, it has a broad dynamic range. This means hBN sensors can work effectively over a much wider range of magnetic field strengths, even if the field isn't perfectly lined up with the defect. This is super important when you're studying things like tiny ferromagnets that can produce strong, randomly oriented magnetic fields. Some hBN defects keep working well even in fields stronger than 50 millitesla, no matter the direction. Third, enhanced spatial resolution. Remember, hBN is a 2D material, Scientists can peel off flakes that are just a few atomic layers thick. This lets the sensor get incredibly close to whatever it's measuring. We're talking about distances so small they're approaching the atomic scale. Something really hard to do with bulkier 3D materials like diamond. Fourth, it works at room temperature. No need for super cold, complex setups. This makes experiments simpler and opens up a much wider range of possible uses. And fifth, versatility and integration. hBN is relatively easy to handle and can be combined with other materials, including other 2D materials, to create what are called van der Waals heterostructures. This opens up awesome possibilities for building sensors right into devices to watch them work, or for imaging complex material systems. People are even developing ways to make arrays of these hBN quantum sensors for high-resolution magnetic field imaging and exploring fiber-integrated sensors for remote sensing. Let's dig a little deeper into how these hBN sensors actually work using that ODMR technique I mentioned. So you have these spin defects in hBN, like the VB- or certain carbon-related ones. First, you shine a laser on them, which aligns their spins. This is called optical polarization. Then, you apply microwave radiation. If the frequency of these microwaves perfectly matches, the energy difference between the spin states an energy difference that changes based on the external magnetic field. The spins will flip. This flip causes a change in how much light the defect emits, its photoluminescence. By sweeping through different microwave frequencies and watching the brightness of the light, scientists get a spectrum, a sort of fingerprint, that directly tells them about the local magnetic field. They can even use more advanced techniques, like pulsed sequences, with cool names like Rabi oscillations, Ramsey interference, and Hahn echo, to get even more detailed info about the spins and how they're interacting with their surroundings. It's not just magnetic fields either. Researchers have used these hBN spin defects to sense magnetic noise, temperature, strain, the spins of atomic nuclei, and even paramagnetic spins in liquids. The VB- defect, one of the most studied, was first spotted using ODMR back in 2020 in hBN that had been zapped with neutrons. Since then, scientists have found various ways to create these defects, like using ion, electron, or proton irradiation, and even femtosecond laser writing. More recently, a carbon-based defect in hBN has shown amazing promise for vectorial magnetometry because of its low symmetry and great excited state properties. It's super sensitive and has that wide dynamic range we talked about. And there's another newly discovered carbon-based defect with a spin-half system that might allow for magnetometry with no blind spots at all, meaning it can sense fields from any direction. This growing family of defects is really expanding the quantum sensing toolkit. This field is moving incredibly fast. Just recently, research highlighted an * Nature Communications * in May 2025. Yes, we're talking cutting edge here. Why that Cambridge team really emphasized how good carbon-related spin defects in hBN are for vectorial magnetometry. They pointed to the low symmetry and favorable optical rates in these defects as key for getting that large dynamic range, and the ability to sense in 3D. They demonstrated sensitivities down to sub-microtesla per root hertz, even with strong off-axis magnetic fields over 50 millitesla. Other research is focused on making these hBN spin defects stay coherent for longer. Coherence time is crucial for sensitivity, especially for measuring changing, or AC, magnetic fields. Special techniques called dynamical decoupling have been shown to extend these coherence times by a huge amount. And it's not just about the defects themselves. There's a big push to improve how these quantum sensors are made and controlled. This includes developing methods for producing large, wafer-scale thin films of hBN with just the right thickness and optimized ODMR properties. This is essential if we want to see these sensors in practical applications. Scientists are studying hBN films grown by different methods and how treatments like annealing after growth affect them. Plus, techniques to precisely place these sensor spots with nanoscale accuracy, maybe using something like a helium-ion microscope, are paving the way for super high-resolution magnetic field imaging. So what can we do with these incredible new sensors? The list is long and exciting. In fundamental physics, we could probe exotic magnetic states in other 2D materials and novel quantum materials. In materials science, Imagine characterizing tiny magnetic domains, watching how current flows in nanoelectronic and spintronic devices, or even getting new insights into superconductivity. For nanoscale imaging, we're talking about magnetic field mapping with detail we've never seen before. Biomedical applications are also on the horizon. While there's still research to do, the idea of high-sensitivity, biocompatible magnetic sensors could open doors for studying biological systems. The brightness of some hBN defects is something to consider for looking deep into tissue, but hBN's flat nature and ability to get super close could be a big win for sensing things on biological surfaces. And finally, integrated quantum devices. Because hBN plays well with nanofabrication techniques, we could see these sensors built into complex quantum circuits and hybrid devices. Now, it's not all smooth sailing. There are still challenges. Optimizing how we create and place specific spin defects with exactly the properties we want is an ongoing quest. Understanding and reducing noise and anything that causes decoherence, that loss of quantum information, is crucial for pushing the sensitivity even further. We also need to fully understand the atomic and electronic structure of all the relevant defects to improve their stability and how bright they are. The fact that different defects can have different optical rates, while potentially useful for tuning, also makes consistency a bit tricky. But despite these hurdles, the breakthrough with hBN in nanoscale vectorial magnetometry is a monumental step forward. By tackling major limitations of older technologies and offering incredible spatial resolution because it's a 2D material, hBN is shaping up to be a cornerstone in the world of quantum sensing. So what does this all mean? It means our ability to see and understand the magnetic universe at its smallest scales has just received a massive upgrade. With hexagonal boron nitride leading the charge, we're not just measuring magnetic fields anymore. We're mapping them in 3 dimensions with incredible precision, right down to the nanoscale. The journey into the quantum realm of magnetism, with hBN as our super-sensitive guide, has just become a whole lot more illuminating. The discoveries and innovations this will unlock are something scientists are incredibly excited about, and frankly, so are we. That's all for this episode of Fun Facts Online. Thanks for tuning in, and we'll catch you next time with more mind-bending science.